On March 3, 2026, a paper was posted on ARKiv. 3 authors, Federico Spada, Małgorzata Krolikowska, Luke Dons. A technical paper about orbital mechanics, not the kind of thing that typically makes headlines. The next morning, Avi Loeb, Harvard's former astronomy department chair, read it and published a response. His opening line was direct. The results of this new paper differ from the official NASA report. And then he added something that you almost never hear a scientist say about NASA in public. In writing, with their name attached, he wrote, and I am quoting precisely, "Yes, official statements from NASA can be wrong. Science is a learning experience." That sentence from one of the most credentialed astrophysicists in the world, posted publicly the morning of March 5, 2026, is what this video is about. Because the disagreement between this new paper and NASA's official report is not about a minor calibration detail. It is about something fundamental, the direction of 3I Atlas's non-gravitational acceleration, which way the object is being pushed, and whether that push is consistent with outgassing from a natural comet or whether it requires a different explanation. The new paper says 3I Atlas is being pushed sideways. NASA says it is being pushed away from the Sun. These are not the same thing. They do not point to the same origin. And one of them has implications that are significantly harder to explain with conventional cometary physics. Today we are going to build this from the ground up. What non-gravitational acceleration is, why it matters, what NASA's model says, what the new paper says instead, why the difference changes the picture, and what the 3 mini-jets at 120 degrees have to do with all of it. This is real science, published this week. Stay with me. What non-gravitational acceleration is and why it matters. To understand the disagreement, you first need to understand what non-gravitational acceleration actually is, because the term is technical, but the concept is straightforward, and it is one of the most important measurements we can make on a comet. When a comet moves through space, it is subject to gravity, the sun's gravity, the planet's gravity. These forces are calculable with extraordinary precision. Given a comet's position and velocity at any moment, you can predict exactly where it should be at any future moment, accounting for all gravitational forces. But active comets don't follow the purely gravitational path exactly. They have an additional push. When a comet heats up near the Sun, its ices sublimate. Gas escapes from the nucleus surface. That escaping gas acts like a rocket exhaust. It pushes the nucleus in the opposite direction. If gas is escaping preferentially from one side of the nucleus, the push is directional. The nucleus accelerates slightly in the direction opposite to the gas flow. This push is tiny. The Spada paper describes it as approximately 1 micrometer per second squared at Earth's distance from the Sun. For reference, that is about 1% of the width of a human hair of acceleration per second. Negligible for most purposes, but over weeks and months it accumulates, and it is measurable with precise astrometry. The standard framework for characterizing non-gravitational acceleration, developed by Marsden, Sekanina, and Yeomans in 1973, decomposes the acceleration into 3 components. A1, the radial component, pointing away from or toward the Sun. A2, the transverse component, pointing along the direction of the object's motion. A3, the normal component, pointing perpendicular to the orbital plane. For a typical comet with outgassing driven by solar heating, the dominant component should be A1, the radial component, away from the Sun. Solar heating is strongest on the sunward face of the nucleus. Gas escapes most vigorously from the sunward side. The reaction pushes the nucleus away from the Sun. The radial component dominates. This is what NASA's official report says about 3I Atlas. A1, the radial component, is 5 times larger than A2, the transverse component. consistent with a comet whose activity is primarily driven by solar heating producing a push directed away from the Sun. The new paper by Spada, Krolikowska, and Donis says something different. What NASA's official model says. Let me be precise about the NASA JPL report before we get to the contradiction, because understanding exactly what the official position is makes the disagreement clearer. NASA's Jet Propulsion Laboratory maintains the Small Body Database, the authoritative catalog of orbital parameters for all known solar system objects. The 3I Atlas entry in that database includes non-gravitational acceleration parameters derived by Davide Farnocchia, a NASA JPL orbital dynamics specialist. The JPL solution is based on 782 carefully vetted astrometric observations. Farnocchia's team selected these observations from the full dataset, applying their standard pre-processing and error modeling procedures. The result is a set of A1 and A2 parameters in which A1 is approximately 5 times larger than A2. What does A1 being 5 times larger than A2 mean physically? It means the dominant push on 3I Atlas is radial, away from the Sun, consistent with standard cometary outgassing driven by solar heating. The transverse component exists but is secondary. This interpretation is the natural one for a comet. It is what you expect from an object whose activity is driven by sunlight hitting one face of a rotating nucleus, causing gas to escape and push the nucleus in the opposite direction. It is the simplest explanation, and it is what NASA's official database reports. The new paper uses a larger data set, 7,788 reported astrometric epochs spanning from May 8, 2025 to February 19, 2026. More than 10 times the number of observations used in the JPL solution. And critically, this dataset includes post-perihelion observations that the earlier JPL solution lacked or weighted differently. The difference in the dataset is significant because the pre-perihelion and post-perihelion phases of a comet's orbit sample different aspects of its activity. An asymmetric nucleus, or one whose outgassing behavior changes with distance from the Sun, will produce different apparent acceleration signatures at different orbital phases. More data, covering a longer arc, gives a more complete picture. What the new paper actually found. The Spada, Krolikowska, and Donis paper, posted on Archive on February 28 and highlighted by Loeb on March 5, derives a fundamentally different picture of 3I Atlas's non-gravitational acceleration. Their most comprehensive analysis finds that the radial component A1 and the normal component A3 are broadly consistent across all their orbital models. Those two components are robust. They are not in significant dispute between their analysis and NASA's. The difference is in the transverse component, A2, and here the gap is substantial. Where NASA's solution shows A1 being 5 times larger than A2, the Spada paper finds the radial and transverse components to be of similar magnitude, not 5 to 1, approximately 1 to 1. This is a major difference, not a refinement, a qualitative change in the picture of how 3I Atlas is being accelerated. A1 and A2 of similar magnitude means the push on 3I Atlas is not primarily directed away from the Sun. It has a substantial component directed sideways. Along the direction of motion, the object is being pushed radially outward and transversely simultaneously, with comparable force in both directions. Loeb's post summarizes this precisely. He writes that the new paper suggests 3I Atlas is pushed sideways and not simply away from the Sun, as implied by the official NASA analysis. The paper's authors are careful about the A2 uncertainty. They note that the transverse component is more sensitive to data selection, parameter correlations, and orbital phase coverage than the radial and normal components. It is the hardest of the three to pin down precisely. Different data selections produce different A2 values, and the systematic uncertainties are larger for this component than for A1 and A3. But the conclusion of their most comprehensive analysis is clear. When you use the full dataset, including post-perihelion observations, and apply rigorous statistical methodology, the transverse component is not negligible relative to the radial one. It is comparable in magnitude. Why the direction matters: solar heating versus something else. Now I want to explain why the direction of the non-gravitational acceleration matters so much, because this is where the scientific implications diverge significantly. Standard cometary outgassing driven by solar heating produces a primarily radial acceleration. Solar radiation heats the sunward face. Gas escapes from the sunward face. Push is directed away from the sun. The radial component dominates. This is the expected signature of a natural comet responding passively to solar energy. A significant transverse component, comparable in magnitude to the radial component, is harder to explain with this model. Transverse acceleration requires outgassing that is directed along the orbital velocity direction rather than away from the sun. This can happen, but it requires specific geometric configurations that are not the default for solar heating. How do you get a large transverse component? There are two main ways. The first is a strongly asymmetric nucleus with localized collimated jet sources positioned at specific latitudes relative to the spin axis. If the spin axis is oriented nearly toward the sun, the jets that are most active, the ones receiving the most solar radiation, are at high latitudes relative to the orbital plane. Their outgassing direction would have a significant component along the orbital velocity. The transverse acceleration would be large relative to the radial one. This is actually what Loeb's earlier papers with Tony Scarmato found. High-resolution Hubble images processed to remove the symmetric coma glow revealed 3 mini-jets at exactly 120-degree separations, plus a prominent sunward anti-tail jet, with the jet system wobbling periodically consistent with a spin axis oriented within 20 degrees of the sunward direction. Loeb explicitly connects these two findings in his March 5 post. He writes that such a configuration, jets at high latitudes with a near-sunward spin axis orientation, naturally favors strongly directional gas and dust emission capable of generating a transverse acceleration component comparable in magnitude to the radial one. In other words, the new non-gravitational acceleration result, with its large transverse component, is physically consistent with the jet geometry that Hubble images had already revealed. The two pieces of evidence fit together. The second way to get a large transverse component is more exotic: active propulsion directed along the orbital velocity, a push not from natural outgassing, but from a directed, controlled thrust. Loeb does not claim this is the explanation. He frames the question carefully. The 120-degree symmetric mini-jet system remains enigmatic, he writes, and whether it constitutes a technological signature of thrusters, we do not know. He is not asserting technology. He is keeping the question explicitly open, but the question is there, and it deserves to be examined honestly. The 120-degree jet geometry, the piece that connects everything. Let me spend time on the 120-degree mini-jet geometry because it is the physical feature that sits at the intersection of every anomaly we have documented about 3I Atlas. Loeb and Scarmato published 2 papers analyzing high-resolution Hubble images of 3I Atlas using the Larsen-Cecchinina rotational gradient filter, which removes the symmetric coma glow to reveal underlying jet structure. What they found was consistent across multiple observations spanning November 2025 through January 2026. 3 mini-jets around the nucleus. separated from each other by exactly 120 degrees, plus a fourth prominent jet, the anti-tail, pointing in the sunward direction. The mini-jets wobble periodically with a period of approximately 7.1 hours, consistent with the nucleus rotation period. They behave like misaligned beams from a rotating lighthouse, and the spin axis orientation derived from this wobble is within 20 degrees of the sunward direction. Now connect this to the non-gravitational acceleration finding. If the spin axis is nearly sunward, the three 120-degree mini-jets are at high latitudes relative to the orbital plane. Their outgassing directions have substantial components along the orbital velocity. The aggregate push from three such jets, evenly spaced at 120 degrees, would produce exactly what the new paper finds: a transverse acceleration component comparable in magnitude to the radial one. This is the natural explanation, and it is physically coherent. The jet geometry, as observed, is consistent with the acceleration direction as measured. Two independent observations pointing to the same physical picture. But the 120-degree spacing itself remains what Loeb calls enigmatic. Natural cometary jets form where solar heating is most intense. They are not geometrically arranged. They do not maintain perfect 120-degree separations over months of observation. They are not symmetric. Loeb's collaborator Frank Lockien raised the key question in January, and it has not been answered since. Three symmetric jets is the minimum viable configuration of propulsion devices needed to stabilize and reorient an object in three-dimensional space. Human spacecraft thrusters typically come in opposing pairs along three orthogonal axes. Three jets at 120 degrees is a different but functionally viable arrangement for attitude control. Is that what we are looking at? We genuinely do not know. The natural explanation requires a specific and unusual physical configuration that happens to produce the same geometry as an engineered propulsion system. That is not impossible, but it is the kind of coincidence that deserves honest scrutiny. The NASA versus independent researchers dynamic. I want to address the institutional dimension of this disagreement directly, because the framing of NASA's official report versus an independent paper is not just a scientific dispute. It reflects something important about how science works and how it sometimes fails. NASA JPL's official non-gravitational acceleration solution is based on 782 carefully vetted observations. The SPADA paper uses 7,188 reported epochs. That is a factor of 10 difference in dataset size. Why did JPL use a smaller dataset? Because their standard procedure involves careful vetting and pre-processing of observations. They apply stringent quality filters. They remove observations that don't meet their precision standards. The result is a smaller but, by their criteria, higher quality dataset. The SPADA paper uses a broader dataset with a different error weighting and pre-processing approach. Their method captures more of the post-perihelion data, which contains information about the asymmetric evolution of 3I Atlas's activity that the JPL solution may have downweighted. Neither approach is wrong in principle. They are different methodological choices, but they produce meaningfully different results for the transverse component A2, and the question of which result more accurately reflects the true non-gravitational acceleration of 3I Atlas is not yet settled. Loeb's statement that official statements from NASA can be wrong is not an accusation. It is an assertion of the scientific principle that all results, including those from authoritative institutions, are subject to revision when better data or better methods produce different answers. The SPADA paper does not accuse JPL of error. It notes that the discrepancies between their A2 value and JPLs are most plausibly attributable to differences in the preprocessing of observations and the adopted error model, a technical explanation for a real disagreement. But the disagreement is real, and it matters, because A2 being comparable to A1 rather than 5 times smaller changes the physical picture of what is producing 3I Atlas's non-gravitational acceleration. Science is a learning experience, Loeb writes. It is, and the learning, in this case, is happening in public, in real time, 10 days before 3I Atlas makes its final close approach to Jupiter. What the Jupiter flyby can settle. Here is the connection to the immediate future that makes this scientific disagreement urgent rather than academic. On March 16th, 10 days from now, 3I Atlas makes its closest approach to Jupiter. The gravitational deflection that Jupiter imparts to 3I Atlas during that encounter will be measurable with high-precision astrometry from multiple observatories. That deflection is determined entirely by gravity, Jupiter's mass, which is known precisely, the encounter geometry, which is being refined continuously, and 3I Atlas's position and velocity going into the encounter. The position and velocity going into the encounter are constrained by the astrometric observations that feed into the non-gravitational acceleration models. The disagreement between NASA's model and the SPADA paper means there is currently some uncertainty in the precise prediction of where 3I Atlas will be on March 16th and how it will respond to Jupiter's gravity. After the encounter, the situation clarifies. The measured deflection compared against the deflection predicted by each model will tell us which model more accurately described the incoming trajectory. It will constrain which non-gravitational acceleration solution was closer to the truth. Additionally, the Jupiter encounter will produce new astrometric data points that extend the observational arc further. Those data points will feed into updated orbital solutions that will resolve some of the current uncertainty in A2. And there is one more possibility. If 3I Atlas responds to Jupiter's tidal stress by producing outbursts, those outbursts will add to the non-gravitational acceleration signal in a new orbital regime far from the Sun, dominated by CO outgassing rather than CO2. Tracking the object's trajectory closely in the weeks after March 16th and comparing it against predictions will provide additional constraints on the true magnitude and direction of the non-gravitational acceleration. The Jupiter encounter is not just a gravitational event. It is a precision test of our orbital models, and those models are, as of this week, in measurable disagreement with each other. The broader implications, what this disagreement means. Let me step back and address the broader implications of what we have discussed today, because the NASA versus independent paper disagreement is significant beyond the specific technical details. First, it demonstrates that 3I Atlas is scientifically complex enough to produce genuine, substantive disagreements among serious researchers using rigorous methods. This is not a case of fringe speculation versus mainstream consensus. It is a case of two technically credible analyses of the same object reaching meaningfully different conclusions about a key physical parameter. Second, it illustrates how institutional authority in science can sometimes lag behind independent research. JPL's solution is based on standard procedures developed for solar system comets. Those procedures are excellent for the objects they were designed for, but 3I Atlas is not a solar system comet. Its CO2-dominated activity, its unusual jet geometry, its interstellar origin, and its asymmetric perihelion behavior may require modified approaches that the standard procedures do not fully capture. Third, and most directly relevant to the question of what 3I Atlas is, the direction of non-gravitational acceleration is one of the diagnostic measurements that distinguishes natural outgassing from active propulsion. A purely radial acceleration is the natural comet signature. A large transverse component is less natural, requiring specific geometric configurations to explain within the outgassing framework. The new paper finds a large transverse component. The jet geometry observed by Hubble is physically consistent with that transverse component through a natural outgassing mechanism. But the jet geometry itself, with its exact 120-degree symmetry and its behavior that Loeb describes as enigmatic, is not obviously natural. We are not at the point of claiming 3I Atlas is artificial. The evidence does not require that conclusion. But we are at the point of having multiple independent observations, the jet geometry, the non-gravitational acceleration direction, the CO2 to water ratio 4.5 sigma above the solar system trend, the activity asymmetry, the Hill sphere coincidence, all of which are each individually explainable within natural frameworks, but which collectively accumulate into a picture that is at the outer edge of what standard cometary physics predicts. Loeb has been cataloging these anomalies since July 2025. He now counts 15. The new paper adds a 16th. Not because NASA was hiding something, because doing science carefully, with more data, using independent methods, produces results that differ from the first quick answer. And the results keep being strange. March 3, 2026. A paper by Spada, Krolikovska, and Duns is posted on ARCIV, 7th of 188 astrometric observations. The most comprehensive analysis of 3I Atlas's non-gravitational acceleration yet conducted. Its conclusion, the transverse component A2 is comparable in magnitude to the radial component A1. NASA's official JPL solution, based on 782 carefully vetted observations, says A1 is 5 times larger than A2, predominantly radial, away from the Sun. March 5, 2026. Avi Loeb reads the paper and writes, "The new paper suggests 3I Atlas is pushed sideways and not simply away from the Sun." Yes, official statements from NASA can be wrong. Science is a learning experience. The 120-degree mini-jets revealed by Hubble are physically consistent with a large transverse acceleration through a specific and unusual jet geometry with a near-sunward spin axis, consistent but not explained. And whether those 120-degree symmetric jets are a natural configuration or, in Loeb's word, enigmatic, we do not know. In 10 days, Jupiter's gravity will provide new data. The deflection, the new astrometric arc, possibly new outbursts. The models will be updated. The disagreement may narrow, or it may deepen. Subscribe to follow this as the Jupiter data comes in. Share this with someone who thinks the science of 3I Atlas is settled. And drop a comment telling me which finding you find most significant. Because two analyses of the same object are pointing in different directions, literally, and figuring out which one is right may tell us something fundamental about what has been traveling through our solar system for the past 8 months. Science is a learning experience, and 3I Atlas is still teaching.